So, the universe of programming languages, right? What's in a programming language? If you ever had the curiosity of looking at the programming languages page in Wikipedia, you'll see over 1,000 languages there. Why do you think that is? I mean, certainly you're not going to learn 1,000 languages, right? If you think of the languages that are popular, right, there's very few, probably in the range of 10 to 15. There's languages that you hear constantly about, right? So how do you think we got to 1,000?
Because of domain-specific language.
Louder, please.
Because of domain-specific language.
Not so much. So domain-specific languages are a relatively new feature. If you look there, most of the languages, most of the 1,000 languages were actually designed and implemented in the 80s. So that's another strange thing. Well, not so strange, but yes?
Because each of the language has their own features to implement, like they have certain paradigm.
Yes, right? So the reason is that it's a free world, right? So the person who implements, many of them do it because they can, right? And then they try to use the language in a certain way. It gets a little bit of buzz. There's maybe one or two projects using that language, and then the language dies. Right? But obviously everybody thought they would be adding something new, right? And everybody, most of them felt a need to have those features because it served them well in the particular project that they were working on, right? So they were trying to create something, a better tool, right? Most of the languages are actually slight variations on previous languages. They're not fundamentally different, all right? And there's actually many other reasons to create a language, and then some of the famous languages were created for completely different reasons. For instance, why was Java created?
Object-oriented.
Louder, please?
Object-oriented.
Yes, but there were some object-oriented languages before. C++ was extremely popular at the time when Java was created. Make it platform independent, right? That was one of the buzzwords, okay? But what were other reasons which actually made Java a lot more successful? So if you look at Java now, all right, they claim that it runs on many machines. Which, of all the Java code that is out there, would you know what is the distribution on operating systems? For instance, how much of the Java code runs on Linux, how much runs on Windows, and how much runs on, say, Mac? So somewhere around 98% of the code runs on Linux. Okay? So it's not the case that we're producing portable code that would run on all operating systems, right? Most large enterprises, they produce Java code specifically to run on Linux, on back-end servers that are in data centers. Has nothing to do with portability, all right? What else do you think was a reason to create this new language
Java
at the time?
browsers.
Yes, they were thinking of that, yet that wasn't what made them successful. All right? So, let me tell you, right? So one thing was C++ was deemed unsafe for large projects. It had so many features, and it had so many subtle features, right? And people felt the need to be so clever about C++ that all large projects, right, were failing, C++ projects failing. And this is the nature of large enterprises. So from the perspective of a person who hasn't yet worked in the industry, it's a bit difficult to understand. But in large enterprises, what happens is that you have very large teams working on very large projects, long-term projects with millions of lines of code. And it's not a very exciting job. And because of that, coders change projects all the time, right? The team that works on a project doesn't have the same members. That varies a lot, right? Yeah, so it's very difficult for a new person to absorb all the existing code and continue the work. Therefore, you need a language that doesn't have so much subtlety. All right? So Java was, at the time, was called C++, if anybody, maybe you're not that old. All right? A lot of people call it C++ because it subtracted a lot of features from C++. So that was one of the reasons why the enterprise adopted Java so willingly, made it so successful. But also it's because it was created by a corporation, which provided guarantees of support for a very long term, right? And then when Sun Microsystem created this language, it also tried to create customer loyalty, right? So it offered a full range of services, training, books, right, updates, and so on, that hooked people into it, right, and made it a very good business model for Sun. So a language is not just a new tool to solve a problem. It's also a way for a company to make money. The model was so successful that soon after that, Microsoft did what? Created C# with .NET, right? So followed the exact model, fixed a few things, learned a few lessons from the JVM, and created a better version of the same business model, right? So C# and .NET is essentially a business model. So these are not the only reasons why, I mean, solving a problem is not the only reason why we create a language. Languages are created for many reasons. One being addressing corporate branding needs, right? We're also trying to address many types of project management concerns. So managers like to be on the safe side, right? They're always thinking, am I going to find smart enough people to work on my project? Turns out that if you're trying to hire, there are not that many, right? So there's a lot of coders that do not have a university degree, and then if you need 10 people in a team, right, and you know only 2 applicants with university degrees, you're going to have to lower your bar and sort of work with less qualified people, right? So then you want them to use tools that are safer, all right? Allow them to make fewer mistakes. Okay, also we have languages that have been created by very opinionated people who just push their agenda, right? So Ruby is one such example. It has a very strong following, and it's not a particular language that has very sound principles, right? It's a bit of everything just dumped in there. It's not a language that is very fast, but yet it's in widespread use because it has this community of very enthusiastic people, just because they feel part of that community, right? So you can create a language that's just to create a community as well. So that's why we end up with 1,000 languages, all right? What we're going to do, because we can't look at languages from this perspective, and we definitely can't look at 1,000 languages, right? We're going to take a more classical approach, because the mainstream languages, at least until Java came up, were generally created because there was a computational paradigm behind, right? There's a computational paradigm that was sound, was theoretically investigated, was shown to have certain good properties, right? And people created languages, you know, because they thought that was a useful way to think about computation. So we're going to follow mostly that trend when we talk about languages. So I'm saying here that we're taking a classical approach, right? A programming language should follow a computational paradigm. There are several computational paradigms, and I've listed them here. They are mostly historic. Most modern languages are actually a mixture of all. But they all appeared, yeah, I think imperative and functional appeared about 60, 70 years ago. In the 50s, that's, yeah, 60 years ago. Then a bit later, object orientation appeared in the 70s, logic programming appeared in the 60s. Each of them brought in a new way to think about computation, right? I'm not going to go into very much detail here, right? We're going to talk about all these things when we look at those languages. And all of them produced a language that was iconic for that paradigm. All right, so you see OCaml here, alongside with Haskell. The most recent functional language is Scala. Scala is very much an object-oriented language as well, so it mixes functional programming and object-oriented programming in a very tight way. It's a very interesting language. And by the way, it's a language that is on the rise. It's a language that I'm using at work. And it's one language that you might want to learn instead of Java, because it's what the language that is likely to replace Java in the future. Another orthogonal sort of concern is concurrency, right? So on top of all the paradigms that we've seen, right, we want to languages will try to handle the concurrency in some way, right? And the degree to which what that happens as a prime feature of the language varies. There are two languages that treat concurrency as first-class citizens, right? One is quite old. It's Erlang. You perhaps might have heard of it. It was a language used by Ericsson in the telecommunication company to code on telecom switches, right? And it was an extremely powerful language in ensuring fault tolerance. So it was one of the most fault-tolerant system at the time. Very recent language is Go, created by Google. Unlike Java and C#, Go doesn't seem to follow the corporate branding business model that the other two languages had. It seems to be a language made just as a good tool with very good support, and it's also a language that is rising. It has higher and higher popularity. In Singapore, there's one startup that is using Go extensively. That's Grab. Okay, what do you know from? You went there. Uh-huh. It's an interesting company to visit. So if you ever have a chance, try. And we have everything else, right? Most of them are called scripting languages. Though if you look very carefully at Python, in my time, scripting was an interpreted language, right? We're going to talk about interpretation and compilation soon. Interpretation being the lower form of processing a language, executing a language. And we're introducing, all of them are put in there and are typically called scripting languages, though they are no longer really interpreted. So Python and Ruby have virtual machines, and JavaScript is just-in-time compiled inside a browser nowadays. Of course, if you're using Node, then yeah, JavaScript is interpreted, but inside the browser, JavaScript is just-in-time compiled. So not sure to what extent scripting applies. There are languages that have their own history. So for the first two, somebody had a vision and tried to pursue that vision, both for Python and for Ruby. Python was created as a simple-to-learn programming language, right? Its author was frustrated with having to learn C, I think, or some language, and decided, I want something that looks very much like pseudocode, because that was the simple way to learn programming, and created Python. And because a lot of kids learn Python in high school, they get very attached and they like the community and they stay inside that community. Python is a very popular language, as you know. JavaScript was sort of an accident, right? And continues to be a big accident. I tend to think about it as the assembly language of the web. Right, it's a language in which you shouldn't have to write code by hand ever. It's a misfortune that it is what it is, but it is what it is, right? So you can't, at this point, you can't change JavaScript. You can't ignore JavaScript, right? Likely, if you work in the industry, at some point you're going to at least generate some JavaScript that executes in a browser. The good news is that there are better and better tools that generate JavaScript nowadays. And I was telling you about that language, Scala. So Scala has a port to JavaScript, can compile to JavaScript, and can execute inside a browser. I would say that's a much better solution than writing JavaScript by hand. Oh, really? Okay, that would be interesting to. Yeah, so I think that would be a very cool way to nowadays to actually teach compilers and to use JavaScript as a backend. because on one hand, everybody needs to learn JavaScript. I don't have. I mean, if you don't know it yet, start learning it. Not with the purpose of writing code by hand, as I was telling you, but you have to know it. There's no. You're gonna, see bugs, see errors. You're gonna see code from other people, right? It's not. You can't ignore it. Cool. So domain-specific languages. These are just a few examples, and there are many more. I literally made up this list off the top of my head a couple of days ago without actually looking at any authoritative source. I probably should have done that. But some of the DSLs are very old, like SQL, right? And you have various areas like query languages. A much newer type of query language is GraphQL, which is usable over the web. But there are many more query languages. You might have heard of HQL, the Hadoop query language. There's a SQL where RES stands for something else that is used in Cassandra, which is another type of database, and so on. We have document description languages. You're obviously familiar with PDF, which, if it's uncompressed, it actually is a text file. I don't know if any of you ever tried that, to uncompress a PDF and look inside, right? It's just a text file. PostScript, which is the precursor of PDF, was the way to encode documents before PDF. We have LaTeX, which is what I use to generate the slides. All right, there's HTML, of which you know, of course. There's an older variant of markup language called SGML. We have hardware description languages. We have UI description languages for .NET. .NET uses this XAML, which is actually a variant of XML. Software testing languages, Cucumber. There's deployment languages like Ansible, and so on. And also very many large institutions, large corporations design their own, but they're generally closed source, right? They want to own the copyright on those. Financial products can be described in DSLs. Risk modeling can be described in DSL. And transaction engines are described by rule-based languages. Yeah, so we're going to try to take a peek at that universe towards the end of the module. Let's talk a little bit about language processing. So we're going to introduce these T diagrams, which are going to allow us to sort of have a pictorial description of language processing steps, which will help us understand in a better way the relationship between different entities involved in language processing. So that pentagon you see over there is a processor, right? It's something that executes code, and a processor is just a language processor. It's not, right? The CPU is just a language processor. It executes machine code, and the machine code is just the language, right? So don't be tricked into thinking that the CPU is this entity that performs this magic, and it's just an interpreter, all right? That interprets very simple instructions, right? The instructions, each of them has very low power, so in order to do anything useful, it has to execute a lot of them, right? But does that very fast, and it's nothing but a language processor, all right? Now, we're going to have the notion of a program, which is a set of instructions. And that set of instructions has to be written in some language. And, right, the language for the 586 processor is the x86 machine code, right? So we're saying here that the Fibonacci code is written in the x86 machine code. And whether that's been written by hand or that's been produced by an automated tool, that's beside the point. Right? It's still a program that has that exact meaning. Okay? And then we're going to take the program and execute it. And we're going to represent that by this diagram over here, right? The program is placed on top of a processor and gets executed. And notice the fact, well, I wrote 586 here and x86 here, right? But this must be a language executable on this architecture, right? So we want to have a correspondence between these two entities. Is this clear? Yeah, simple stuff, right? Now, we're going to introduce translators. We have a variety of translators. So I want you to think about the following, right? All of you know two programming languages, right? Two languages. And you can write Fibonacci in one of the languages. And that Fibonacci code has a very specific behavior, right? You go to the command line, you run it, and it prints a line asking for input. You type the input, and then it prints the output, right? So you can write another program in a different language having the exact behavior, the exact same behavior, right? Printing a prompt, accepting input, printing the output, right? If you run them from the command line, you wouldn't know in which language one was, the program was written. And if you look at the two programs side by side, the natural question arises, can the translation from one to another be done automatically? Right? Not necessarily a translation between this version of the program and this version of the program, but between this version of the program and a corresponding program having exactly the same behavior. Right? Can that be done automatically? Everybody should answer yes to this, right? It's obvious that it's possible. So language translation is automatable, right? And the translator, right, is the tool that performs that kind of operation, right? It translates from language to a to language, okay? And typically we can translate between any two languages, but we're mostly interested in translations between a high-level language to a low-level language, right? Why is that? Well, the hardware, all of you have some background in computer architecture, right? Have seen some machine code, have seen some assembly language. You know the power of the typical machine code instruction, right? And you know that you have to execute very many of them to do anything useful, right? So you want to avoid that language, and you create a language with higher order of abstraction, right? And you're interested in translating that higher level language into the low level language. Then you go and create a language with even higher level of abstraction. And you're interested in translating from that language into your previous language. And a lot of translation was done like that. So for a long time, cheap compilers will have C as an intermediate language, right? So the compiler for C existed in Unix as part of the operating system. And very many compilers, I'm not sure about OCaml, but Haskell, for instance, I know for sure that for a while it took this route. It wouldn't compile directly to machine code, but it would compile to to C, and then invoke the C compiler in the background and translate further, right? So we're looking at successive translations from a very high level language, right, up until we get to the lowest level of the machine code. So that's the compiler's job, high level to low level. It's possible to do the reverse, to compile from low level to high level. That's a decompiler. Decompilers are not so useful. They're usually used to reverse engineer code. In today's world, with a lot of open software, you might as well go to the author and ask for the source. Not so useful to use a decompiler, right? We're just emphasizing the fact that it is possible technically to do that. All right, so how do we represent a translator? We use this T block, which gives the name to the T diagrams, right? We take a language. So the input is a program in a language, and the output is another program in a different language, and this translator runs, or this compiler was written in this language, right? And in order to make it run, I have to add a pentagon at the bottom here, the 586 processor. At that point, it would be running, right? But currently, this is just a translator. Notice the following interesting fact. that what we perceive as a program, let's say in BASIC, is actually data for the compiler. So we have a duality between code and data, right? We write Fibonacci in BASIC, and for us it's code. But for this translator, that Fibonacci code is data. It's the input data, right? It's a file that is read in, processed inside, and another file written in C is spit out. So what we would perceive as a C program is actually output data for the compiler. Is this clear? Right? So this duality is important to understand. Okay, so we can have a translator from OCaml to machine code x86, which was written in machine code. Whether it was written by hand or it was generated automatically, that doesn't matter. Nevertheless, the language, if I open the file that represents this translator, I'm going to see binary code. Okay? The input would be an OCaml file. The output will be an x86 binary file. Right? So we can have that. Now, OCaml is a language that happens to have a virtual machine as well. It's a platform that happens to have a virtual machine as well, right? So you have the option of compiling directly to a native code or to bytecode, to virtual machine code, right? And that virtual machine language is called bytec, all right? And we would have a translator from OCaml into bytec, right? Written in the language of x86. All right, so if we put a pentagon underneath, we would have a running translator. All right, so let's put all these elements together, right? So our original Fibonacci written in BASIC, right? Let's look first in the middle, right? In the middle we have a translator, but because we have plugged in a processor here, we have a running translator. It's not just a piece of, that's not a binary file anymore, it's a running process, right? And then the input to that process is a Fibonacci written in BASIC. It's a file, right? And the output of that process will be Fibonacci written in C. Okay? So this diagram represents the translation process. And we can have this in stages. We take Fibonacci in BASIC, put it through the BASIC to C compiler, which is a process, right? We get the C output, which is further input into a C to x86 compiler, right? Again, running, right here. And we get Fibonacci in native code. So this is a file where we can plug in an x86 processor underneath here, and we can have it running. It cannot be part of the same diagram, but this element now, we can put the x86 processor underneath and run it. Now, another very interesting thing to understand and remember is that a compiler should always compile itself, right? Let's think a little bit about the process of creating the first language. Let's say that C was the first language, right? Even though that was Fortran. But let's think of C, because at some point they actually have done that process. So they created they had this PDP machine. They were thinking about creating an operating system, which operating system became Unix, and they were thinking, oh, we shouldn't write this in machine code. We should invent a language that should make our process a bit easier, right? So what did they do? They wrote a C compiler. They first invented the language, right? But they created a C compiler and wrote it in machine code, right? So that was version 1 of the compiler. They worked very hard. They had to write directly in assembly language, actually, right? Not really machine code. In assembly language, they wrote the compiler, they had it running, right? And then, what do you think they did for the version 2 of the compiler? They chucked away, yes?
They wrote it in C code?
Yes, so they chucked away the assembly code. They rewrote it completely in C. Why? They already had a C compiler, right? So version 2 of the compiler in C is compiled using version 1 of the compiler, which was written in assembly language. The result of this compilation is a binary representing a compiler that can run on that architecture. So then we do what? We compile the same compiler by itself. So version 2 of the compiler gets compiled by version 2 of the compiler. At this point, it's possible. I already have the binary, right? Which accepts C input, which is the language in which the compiler itself was written. So the compiler should always compile itself in order to take advantage of all the improvements that were implemented in that compiler. Have you ever compiled GCC from scratch? Right, so yeah, one guy getting his hands dirty. So there was a time long ago, right, when there was no other way to install. So now you do apt-get, right, install GCC, and that's it, right? No, you would download GCC from GNU, right? You would untar it, and you would compile it, and that would be a process that would take half a day. And you would notice at some point that the compiler has finished. So the current version of the compiler, or the new version of the compiler, would be compiled with the old compiler already available in the operating system, right? And then at some point you would see that the compiler would compile itself. The new version of the binary replaces the old version, and then it goes through the entire process using the new version of the compiler, right? So the compiler compiles itself. And it was a very interesting thing to see at the time, right? So took a while to actually figure out why it was necessary to do that. So this is the process of bootstrapping a compiler, right? We don't have the versions here, but actually the second round of compilation, we would have the same versions here, right? So this is the OCaml compiler written in OCaml, right? Which has already been compiled once, and now we put it through again, through itself, to obtain another version of the compiler, right? So these two things, they have the same behavior, but they're not the same binary, right? This one has all the improvements of the new version, whereas this one is the old version, all right? Cool? All right. So remember that. We're going to come back to it at some point. Any questions so far? No? All clear? Simple stuff, right? Yes?
I still don't kind of understand why it needs to compile itself to produce it for the new version using the.
Well, so the new version implements some improvements, right?
You mean the new version compiler?
The new version compiler,
Okay.
right? So the new version.
Yeah.
Okay, cool. You would like the compiler to take advantage of its own improvements, right? That's the. All right. So we talked about compilers. Interpreters are programs that execute another program, all right? So we don't produce an output that is another program, right? We just treat the input as, the input program as data, right? And the interpreter goes through that file over and over and over, right? And looks at all the instructions, and as it encounters each instruction, it executes it. It performs the actions of executing it, right? So let's say that in your input language, your printing instruction is called print. And now your interpreter is written in a language where the printing instruction is called write. So this interpreter will take this as an input file, will keep scanning it and trying to execute. Every time it says print, it will execute write, essentially. It will not generate a write line of text into an output file, but it will actually physically directly execute write. Is this clear? So that's an important distinction. Depending on the level of processing that an interpreter does, interpreters tend to be slower than compilers, right? But they have two advantages. One, you don't have to know two languages, right? So you're inventing a language. Typically, that's your invention. You have to write if you're writing a compiler, you have to write a compiler in some language, and you have to generate code, typically for some architecture, which is a third language, right? So you have to know assembly language or machine code pretty well in order to be able to generate executable code, or maybe C, right? Whereas if you're writing an interpreter, since you're executing directly, right, there's no need to know another language. Interpreters can actually be very efficient, right? So depending on the level of processing, you can take the input file and produce a very efficient internal representation, and then work with that and actually have the program run quite fast. But most interpreters actually don't do any kind of processing. They just keep reprocessing the input file in a text format, right? And because of that, they tend to be very slow. We call the interpreter source language the language in which the interpreter is written, and then the target language is the language that the interpreter can execute. And an interpreter is just a box, right? So remember, we were writing boxes like basic that is written in the language of x86, right? Right, this is essentially the basic interpreter. So the basic interpreter would be written in the x86 language. So if I put a pentagon here, it becomes a running process, right? But it doesn't translate from left to right. I can put something on top that has been written in BASIC, and it gets executed right away, right? And I was telling you that a processor is just an interpreter for machine code, and there's no distinction there, right? BASIC is an interpreter for basic code, right? In a similar fashion, we can have an OCaml interpreter. Does there exist one, actually? I see. So there exists an OCaml interpreter. OCaml seems to have to be pretty common.
Scala also have a
Scala actually compiles in the background, so performs a translation in the background, and then literally invokes the compiler as a library and executes JVM code. I mean, there's no.
There is a compiler to JVM code,
Mm-hmm.
and then you get JVM code that will be very portable for Scala.
Mm-hmm.
But I think there's also an interpreter for Scala. You can run that interpreter.
The REPL is not. I mean, yeah, it looks like an interpreter. It has a REPL, but then every expression gets compiled in the background. It's incrementally compiled. But I thought OCaml was doing the same thing. So OCaml, when you press colon colon, semicolon semicolon, right? Actually, that gets compiled and then executed. It's not really interpreted. Because nowadays compilers are libraries, so you can just link them in, and you can enjoy the properties of sort of an interpreter, meaning that you can dynamically compile code, but still compile code that executes in the end.
So it looks like interpreter, but actually it's semi-compiled.
Yeah. So this is how we would execute an interpreted program, right? We have Fibonacci written in BASIC. We have a basic interpreter written in x86, and this can run on this processor, right? So if we look at this thing, right? Maybe I should try to emphasize it on the slide so it is available in the recording. Right, so if we look at this thing, it looks like a pentagon, right? And it looks like a basic processor. I could try to hide this away, and I'm gonna say basic. Well, my writing, does it look like basic? Not much, huh? But just imagine that's basic. So you can essentially hide away abstract away the processor, and you can say, oh, this is a basic processor. Okay? And you can plug it underneath everything that has basic. And this is the beauty of these diagrams, because you can compose things and they sort of keep their shape, right? And then you can decide to hide away details and sort of look at them as new building blocks for something else. All right. And the interesting thing is that hardware gets emulated nowadays, right? So I have no idea what this is, the PC, but it's probably a piece of hardware that can emulate the x86 architecture. So it can execute x86 machine code, right? So therefore, that emulator is going to become an interpreter for x86 code. We have this processor, we have this interpreter from x86 into that processor. This is a hardware interpreter, right? It's not written in software, it's hardware. And then we have a Fibonacci program that is written in x86, possibly a result of some compilation, and we can execute that, right? And with today's virtualization, this is a very common thing to happen. We execute, we have these Windows binaries, for instance, and we see these Windows virtual machines or Linux virtual machines in the cloud, but you don't really know what the hardware is underneath, right? Most of the time, the processor is emulated. All right, let's look at a typical execution of a Java program. So now you see everything side by side, sort of, right? What happens with JVM is that it has two phases, right? There's a bytecode compiler, and similarly, and there's a similar process for OCaml, right, which has a virtual machine as well. So the compiler only translates as far as the JVM, right? And we produce JVM bytecode, and this is the process represented here, right? And then we have to execute that, but that is an interpretation. The JVM code gets interpreted by the JVM machine, which is a JVM interpreter. Okay? Now, because the JVM has a very good representation, internal representation of the code, it happens to be reasonably fast, right? So that's one example where interpretation actually doesn't slow down significantly the program. Okay. These slides, I was telling you that I'm using LaTeX. All right, so we translate from LaTeX to a format called DVI. Stands for device independent. This translator, it's a compiler, runs on x86, right? We produce a DVI file, which is further translated into PostScript, right? Again, running on x86. And the PostScript file is further translated to PDF, right? So it's a three-step translation. It very much illustrates what I was telling you previously, that you go from a high-level language to something lower, which is further translated to something even lower, which is further translated to something even lower. Actually, if you would want to argue, this is lower level than this one, right? So this is sort of a convenience translation because the PDF is so popular. But if you look at the power of the language, PS is probably a lower level language than PDF. PS is still a language that is available in printers. Most of the laser printers speak PS, PostScript. You can just send a PostScript file and they will print it straight. Which I think also happens with PDF. So many printers actually understand PDF directly too these days. Now, the Acrobat reader that you saw me starting at the beginning of the class will do exactly that. Takes the PDF file, the PDF to x86 interpreter is actually Acrobat reader, and it executes on x86, and we get to see the slides. So this was pretty much what I had in mind for language processing. All right, so we've talked about T diagrams, we've talked about interpreters and compilers, and it's time to move on. Any questions so far? Yes? Again?
How you generate the PDF, right? There are so many intermediate steps. What do you do that from?
Because nobody wanted to aggregate everything in a single step. So different people produce different steps. Some of them are historic. So many years ago, the DVI format was the single output well, actually, it wasn't really the single output. You would have drivers from DVI to various printers. So the next thing you would invoke, screens were not that good. Most of them were text screens. And the only good way to see a document was to actually print it. So you would translate LaTeX to DVI, and you would have various programs to translate DVI to various printers and send them directly to those printers. It would happen typically on a Unix system, and you had to know which printer is connected to which port and specify a lot of information in order to get your file printed. Later, PostScript appeared as a printer language, right? So that's how it appeared first. And then it was possible to send the PS file to a printer. So the only driver you needed for DVI of the many that existed at the time was the DVI PS driver, right? Which is what we're using still now. And even later, the PDF format came up, right? And nobody really, I don't think that I'm actually running these three commands. I'm running a command called PDF LaTeX, which in the background is performing all these steps. But nevertheless, it's three separate binaries that get invoked. It's three separate processes that are running, right? And it's simply because nobody wanted to go back and change this that was running very well, or change this that is running very well, right? Every time a new thing appeared, it was more easier to just create an add-on and put it in the chain, right? And that gives us flexibility, right? I mean, in a lot of situations, things just happen like that. It's the minimal effort. You don't want to spend too much effort for something that, if you have something that already works and only needs a little bit to be adjusted to a new situation, you're just going to spend that little effort. You're not going to start a project from scratch and spend a lot of money and effort to have something that could be obtained with much less effort.
Another reason could be the modularity. If you structure a big task into separate components.
Yes, of course. Yeah.
Get better reuse on it.
Yeah. No, but you see, when you look for modularity, you don't necessarily look at the level of separate binaries. So you can have modularity inside the code, right? But if this project would start now with let's create a document description language, you would get a PDF output directly. Nobody would think of translating into DVI because there's nothing else to do with DVI but to translate it into PS or PDF, right? You don't have those many printers that would, benefit from a DVI format. But yeah, obviously you need to have modularity, and probably inside the code organization, inside that binary, you would have a very clear isolation of the various tasks and the various translation steps. Yeah. But my guess is DVI, LaTeX to DVI. LaTeX has not changed for, 20 years? So LaTeX is one piece of code that was created about 4 years ago, and nobody changed it for 20 years. It's based on a piece of code called Tech, created by Knut. Donald Knut, right? You know who the guy is. So that he was so confident that there are no bugs in that he offered to pay $2.56 to everybody who would find a bug in Tech, right? And actually, there were a few people who very few bugs were found, but there were very, very few, right? And people did not cash those checks, so he sent everybody a check. They didn't cash their checks; they framed them, and they hung them on the walls, right? So those are pieces of software that were extremely well written, so nobody wants to touch them, right? What you want is to add on something that just pushes it a little further, right? But you don't want to tweak something that already works very well. Yeah, if it works, don't fix it. That's a saying. All right, so we're going to benefit from a refresher on some math concepts, namely inductive definitions. You're all familiar with induction as mathematical induction, right? You all remember that. What is it? If you want to prove something about all natural numbers, right, you prove that it holds for for all numbers starting from a certain number, right? Most typically you pick 0. So you prove that it holds for 0, And then you prove that for all numbers greater than 0, whenever it holds for n, it also holds, that implies that it holds for n plus 1, right? And then you essentially have a chain of reasoning. So let me make that a little bit clearer, right? So you prove that P of 0 holds. So the statement for 0 holds. And then we prove that for all n, Pn, for all n greater or equal to 0, right? Pn implies Pn plus 1, right? So then we're going to have a very simple chain of reasoning. Because P0 holds, it must be, when n is 0, it must be that P1 holds, right? So we have that P0 holds. We know that from the first proof. And then because of this, via modus ponens, we know that P1 holds. Once P1 holds, I plug 1 here, I get 2 here, right? We know that P2 must hold. And I can go on and on and on, right? So the result of this is that for all n, Pn holds, right? This is the principle of mathematical induction. So we prove these two things, and then we get that the result holds for all natural numbers. Now, in code, we deal with data structures. Data structures have structure, right? You know, lists, trees, all of them have a certain structure, right? And this structure is typically unbounded, right? Of course, memory is finite, but up front, if I define a tree for you, you won't be able to tell me at which depth the tree should stop. Any depth should be possible, right? Why? Because memory is essentially unbounded, not in the sense of unbounded for the current physical machine, but in the long-term future, you're going to have more and more memory, right? And if you keep the same program running on the machines of the future, you're going to be faced with more and more memory than larger and larger data structures. So if you have a program that accepts, for instance, a tree, you can't really set a limit on the size of your tree. So if you want to prove that your program is doing something useful for that tree, you will have to have a method of logical inference that allows you to infer that property for trees of any size, right? But these trees of any size, actually, they have a structure. They are enumerable. We can enumerate them, right? In the same way we can enumerate natural numbers. So it must be the case that we can have a principle of induction for those, right? And we must be the case that we have a way of defining things for those data structures that would not limit us in size. So this is where inductive definitions are useful. So let's look at the simplest possible inductive definition. This is called the Peano numerals. You can Wikipedia that. This was a mathematician at the beginning of the century, came up with a formalization of natural numbers. First guy who got it right. There were many others who tried. And actually the formalization is very simple, right? He said there exists this element called 0. It's a special element. It must be a numeral. And then we have this function called successor, suc. And then if n is a numeral, so is successor of n. And this is a data structure, right? 0 is a symbol in most languages. And then successor is a constructor. And I can apply it repeatedly, right? If 0 is a number, then successor of 0, single application, is also a number. And then successor of 0 is also a number. And then successor of 0 is also a number. And I can go this way ad infinitum. It's true that we've gotten used to denoting these numerals by 0, 1, 2, 3. But that's just a notation. Internally, structurally speaking, right, natural numbers, well, one way of defining them is by giving them this structure. Okay? So this is a type of inductive definition. Let's look at a definition for trees. We're going to say that empty is a binary tree. So look at it. It looks like a statement. I'm saying something that I consider to be true. Empty is a binary tree, right? And if L and R obviously for left and right, L and R are binary trees, so is node applied to L and R. Okay? And this is a very simple type of tree. There's no, you're used to having numbers inside trees or strings or something. This is a very simple type of binary tree. It only has structure, right? But then something like this, what you see here, right, is a binary tree. It is constructed by the induction rules. So how does this go? Well, empty is a binary tree, and empty is also a binary tree. Therefore, node of empty and empty must be a binary tree. The same here, node empty, empty must be a binary tree. So since this one is a binary tree and this one is a binary tree, this entire thing, according to the rule, must be a binary tree, right? So this is my inductive reasoning at work, right? So this is an inductive definition, right? Notice that whenever we do inductive definitions, we use recursion, right? So this is a binary, this entire thing is a binary tree if the components inside are also binary tree. Looks like a recursive call, right? So we have a form of recursion. The typical way of representing these rules are in this syntax, right? We write a premise above the bar and a consequence below the bar. So we're saying that if n is a numeral, then successor of n is a numeral, right? Some of the rules do not have a premise. So this one does not have a premise. It is intrinsically true, right? With nothing to start from, we state that 0 is a numeral. So 0 is a numeral is an axiom, essentially. It is a fundamental truth of our theory. Whereas this one is a conditional truth. If this is true, only then the consequence is true. Okay? Similarly for binary trees, right? The axiom is that empty is a binary tree, and then if T1 is a tree and T2 is a tree, node of, or TL and TR, TL and TR are binary trees, the node of TL, TR applied to TL, TR is a binary tree. Is this clear? Let me not rush. I'm looking at the clock and I'm a bit tight on time, but let's not rush. Is this the same?
It's a shorthand.
Oh, this is a shorthand, right? So we don't say that they belong to something. We just enumerate them. It's a way of enumerating them. So it's a shorthand form for the same definitions. So now there's an interesting thing. Looking at these rules, can we talk about the set of all numerals? And what would that set be? So actually this is a bit tricky, all right? And it requires a lot more mathematical background, so I'm gonna give you a short version. It turns out that obviously we already discussed, right? So 0, successor of 0 have to be inside the set num. But you see, if I pick an element out of the rest of the universe and make it an element of my set num, I cannot disprove that it is not a numeral. I cannot reach the conclusion, oh, this is not a good number, this is not a good numeral. And moreover, but I also have to add the successors of that number, right? So we're picking out of thin air this symbol called infinity and say, well, this is a numeral. And alongside with it, we're adding the successor of infinity, the successor of infinity, and so on, right? And turns out that this is a set that still follows the rules. So we can't say that this is not the set of numerals, all right? So we need to add an extra element. Now there's a theory that proves, that looks at all the sets that can be considered, given a set of rules, that can be considered the set covered by these rules, right? And there's a hierarchy in these sets. It has a structure of lattice, right? And so there's a bit of a mathematical theory there, and we don't want to go into that, right? It turns out that looking at all these sets that would be correct sets satisfying the rules, there's the smallest one and there's the greatest one, right? So looking from the perspective of set inclusion, right? I will have one at the top, at the bottom, right? Let's call it num, because this is the one we want. And we have some num1, which is slightly larger, some num2, right? These may have some other layer of sets. And then at the top, there's one that is num infinity. This is the largest one that satisfies the rules, right? And because of this property, people decided that the smallest set is the one defined inductively, right? So whenever we use the word inductive, besides the rules, we also say smallest possible set, right? Which is exactly the set that we have given here. All right? There's an interesting theory of co-induction. Not induction, but co-induction. That refers to this set. This set pertains to all infinite data structures that we can write. What do you think it's an infinite data structure? Can you give me an example of an infinite data structure? Yes, so it would have an infinite number of elements. So for instance, it's a string, right? If I put a thermometer reader somewhere and that thermometer keeps sending the temperature every second, right? That's a potentially infinite stream of data, right? Can I compute with it? Yes, of course. I can receive it inside the machine and do something with it, right? How would I represent it as a data structure, right? As an infinite data piece of data structure. How would I store it? Would I be able to store it? Actually, yes, right? As a lazy stream. So if you have heard about the concept of lazy computing, I would have this data structure where new elements are only computed by demand. So at any point in time, I only see a finite amount of them, right? So it is interesting to look at these programs, and from a semantic point of view, what you need is co-inductive definitions to treat those numbers, right? So this is a complete side. It's a detour, right? But what I want to justify here by waving hands a little bit is that what we want to take is the smallest set. It's one that you intuitively would perceive it as the right set, right? If you have a little bit of practice in programming and have looked at data structures, you will never consider infinite trees as representations of programs, for instance, right? We're going to see soon that programs can be translated into abstract syntax trees, right? You would never consider them infinite. So the smallest set of elements is the set of finite data structures for that inductive definition. Okay, so okay, a bit of hand waving here. Are there any questions on this? Hopefully I didn't add to the confusion. Right? So inductive also means smallest, co-inductive means largest. If you're going to do research in programming languages, you'll see the word co-induction very frequently. So we're saying that num satisfies the rules, right? And it's clear. So it's what I was trying to explain. If we look at strange num, it also satisfies the rules. It turns out that strange num is not the largest, the smallest, right? It's actually larger. So we don't pick that by convention. Induction means smallest. So we're saying, yeah, smallest or the least set or the set that contains nothing else. So you're saying it has this rule and this rule, right? The elements provided by this rule and the elements provided by this other rule and nothing else, right? So consider this nothing else clause added to any set of induction rules from this point on. Okay. So this is repeating, right? We are producing here a set that is isomorphic with the natural numbers. It's the simplest example. It's one that we won't be seeing again because we have a good representation for natural numbers in code, right? In hardware, there is a good representation, so we will never need to write the data structure that represents numbers. However, for trees and lists, we always need to provide data structures. And you'll see that the structure is very similar. Okay, maybe I went a bit overboard with the explanations. Okay, so inductive definitions come with an induction principle, right? So let's think about a tree, right? It has left child and right child. Can we adapt the definition that we saw for natural numbers before to the trees? So can I come up with two rules that would give me a way to prove a property about any tree? I want to prove that for all trees, some property of T, for all trees T, some property of T holds. All right? Can we do that? Well, it's relatively straightforward, right? So first of all, I want to prove that it holds for empty, because empty is a tree, so I have to prove that it holds. And then for any trees L and R, if P of L holds and P of R holds, then it must also be the case that P of node LR holds, right? So let's try to write that down. So we want that P of empty holds, and we want that for all L and R that are trees, P of L holding and P of R holding implies that P applied to node LR holds. So you can see the similarity with the induction for the natural numbers. Any data structure you give me, any data structure defined by inductive definition you give me, I will be able to write a similar induction principle. So extended to all possible data structures, this is the principle of structural induction. Okay? We're going to be using it a lot. All right. So let's apply induction just to practice. Let's apply induction to numerals, right? And then maybe we will apply it to trees. So we're saying that the numeral 0 has parity 0, and any numeral successor of n has parity 1 minus p, if p has parity, is the parity of n, right? So the property that we want to prove is that every numeral has either parity 0 or parity 1. Does P satisfy the rules of structural induction? Right? Yes, it does. Right? 0 has parity of 0 or 1. And then if Pn has parity 0 or 1, then P successor of n has parity 0 or 1. Right? So we can formulate the principle of mathematical induction as a principle of structural induction, taking advantage of the new data structure that defines numerals for us. Remember, this is just practice. We will never come back to these numerals again. But let's look a bit at the trees, right? This is what I was telling you before. If empty has property of property P, and if L and R have property P, both of them, right, then so does node of L and R. So let's try to compute the height of a tree and prove that what we are computing is indeed the height of a tree, right? So we want to define the height of the tree based on inductive rules and then prove some property about it. So the height of the empty tree is 0. If the height of the left child is h1 and the height of the right child is h2, or hr, sorry, then the tree node LR has height 1 plus maximum of HL/HR. So these are English definitions, but they definitely have the structure that we have seen in inductive definitions, and we're going to see the inductive definitions shortly. Okay? So it may seem obvious from this that every tree has a height, but it wouldn't be the case if we allowed infinite trees. What excludes infinite trees from our set? The condition that it has to be a minimal set, right? When we say it's minimal, it's the least set, we are actually excluding any infinite data structure that might fit in there. Okay? So this is what makes the definition well founded. So let's prove that there exists such a number h for all trees, right? And we do that by induction. So rule 1, empty is a tree. Does a height exist for the tree? Yes. We have a rule that tells us that the height of the empty tree is 0. So there exists such a number, right? So we have proved the property for the empty tree. Now, let us assume that for any trees L and R, those two trees have a height, right? HL and HR. There exists such a number, right? Then, for the current node of L and R, right, we also have a number, which is also defined in the rule and has this value. So immediately we prove that there is such a number as well. And we have satisfied both of the rules of structural induction for trees, at which point we can conclude that the original property holds. All right. So for those of you who are not yet familiar with OCaml, let's look very quickly at an implementation of numerals in Java, right? So you get a gist of it. Yeah, a little understanding of what's going on. So we're going to have an interface called num, and we're going to have two classes, 0 and successor, both of them implementing the num interface, right? And we don't need to do anything inside 0. 0 just will, an object of class 0 will just exist as the element 0. And then the successor has to implement the successor function, right? So we have a constructor, right, which gets a number, and, right, what's that number in relation to the current number? Is the predecessor, right? So we're going to call it the predecessor. So then we can write two lines of program, create a 0, an instance of 0, and then we can create any successor of successor of successor of 0. Okay? Now we're jumping the gun a little bit. So a similar definition of OCaml, right? So here we define a single type, which is of type of a sum type. It's called a sum type, right? It is either 0 or successor of num. That's what we're saying. When we're writing that definition, this guy becomes a symbolic constant. Automatically, OCaml will record it as a symbolic constant. It's a constant, it has its own value. There's nothing else to identify it. Pretty much as you do with numbers in mathematics. Every number identifies itself. Now, successor will be a function whose argument is num, and notice the recursion. So now the recursion is very obvious, right? We are defining a type in terms of itself. All right? And we can, this is a constant now, right? This is not a class. This is a constant. Whose type is num, right? So I can give this value to any other variable, but I can just use that value as itself. And then I can create any other numeral by successively applying the successor constructor, the successor function, to 0. Everybody is very puzzled.
But there's no definition of successor function.
What would you expect? Like function suk? No, so you don't need one, right? This is the definition. The fact that I mention it here, camel, this is a definition. Okay? So in general, what we define there is a constructor. What's a constructor? Is a way to build a new object, right? But in such a way that there's no other representation for it. All right? So you're going to say, oh, what's the value of the successor of 0? The successor of 0. No. What is in your head, right? Nowhere in OCaml you're going to be able to say successor of 0 equal 1 and have that be true. We are defining a completely new realm, right? One is a hardware encoding of numbers that is available in OCaml because it's so convenient, right? But what we are defining is a completely new realm, the one of numerals. Of course, there's an isomorphism between this new realm and the realm of binary numbers that the hardware provides. But this is a completely new realm. What is the value of successor of 0? This is a bit slow. Successor of 0. I have to write really slowly. There's no other way to express it. The successor of 0 is the successor of 0. That's it. So I have defined the function successor, meaning that it's syntactically possible to write successor applied to 0, right? From the point of saying this here, this is syntactically correct OCaml. But I don't have any other way of expressing this expression. It just stands for itself. You might write a function evaluate, and we're going to see that later maybe. And the value of evaluate might be equal to 1. This would be a function that realizes the isomorphism between natural numbers and binary, the hardware encoding, and their the numeral equivalent, right? So that's the property of a constructor. It constructs a new object, and that object cannot be expressed in any other way. All right? So previously we've seen the same with node. What was the way to express the tree? Well, I had to say node, apply to node, apply to node. I wouldn't have any more compressed form, right? In that sense, node is a constructor, right? It gives me a way to create a new object, but I have no other way to express that object but to say that it's the node of something. And I think we're going to have the implementation here. So this would be the Java equivalent, the Java variant, right? And this is very obvious. I'm sure you've seen it before. So let me show you the OCaml equivalent, which is much more concise. So notice the conciseness, first of all. So now node is an expression, is a constructor, it's a function. Just by writing it here, it becomes a function with 2 arguments, one tree and a second tree, right? Again, notice the recursion. And this allows me to say node, right? This entire expression is syntactically correct now. But I have no other way of expressing that tree. Node is a constructor. Okay? So by having placed a constructor here, I haven't achieved very much because I have not specified any computation. I have specified a syntactic construction that just allows me to create a certain structure. There's no computation in there. Okay? Now, it's very rare that we're going to write trees like this. Most typically, we're going to take something and create a tree out of it, right? And then this construction like this will exist in memory, but we're never going to see it in our face. Or maybe when we debug, we might see some of it. But in general, we don't have to write in our code node of node of node of node, right? Okay. So what we're going to do, what I'm going to do is provide a refresher of OCaml, or for some of you, it's going to be a first encounter with OCaml. I'm going to record that as a video lecture and upload it. That's likely to happen tonight, or maybe tomorrow night. Would be good if you get a chance to watch it before the next lecture. Obviously, you're going to have a lot of opportunity to practice it during the labs. Don't worry too much. Again, you've already learned 2 languages at least, so it's not going to be that tough. Okay, so let's write a height program for a tree in OCaml and introduce more elements, right? An interesting fact, once we have structural data types, is the pattern matching. Okay, so remember, in general, a tree is node, and I can have a very complicated expression here and a very complicated expression here, right? But in this function, I'm going to say, well, given this tree is either empty, in which case the height is 0, or it's a node with a left child and a right child. So everything, this very complicated expression just matches L, and this very complicated expression just matches R. This is a very cool feature available only in functional languages, all of them, right? Very well, I mean, no, not Lisp and Scheme, but all the type ones. And in that case, the definition is going to be 1 plus max applied to height of L and height of R. You might be surprised that there's no brackets here. If you want to put brackets here, you can. We typically don't. We call that a current notation for function application. So f applied to argument x, we write it like this, with a space in between. And we're going to see that there are advantages to that. Okay, so in general, we use this notation. All right, so we're going to delve more into OCaml. I'm not going to tell you how this is evaluated. It's jumping the gun. We can do things properly, one step at a time, when we talk about OCaml. So remember inductive definitions. We're going to look at them over and over and over. They're going to be a staple of our reasoning and of our way of defining things, right? And they are also essential for understanding OCaml data structures. And this is about it for today, I think. So what's going to happen now is I'm going to upload the slides. I'm going to upload the video recording. I'm going to initialize the course, look at your pictures and try to get to know all of you. Do check the forum, and yeah, feel free to say hello. If you have any questions, post them in the forum. Would be great to start some conversation and get the ball running. Do it early. Don't delay trying to revise the material, because I mean, you know how it is. It's always good to start early. So that's about it for me today. Thanks for coming. See you next time.